online faculty, the Department of Mechanical Engineering, BIT SINDRI, on the topic Recent Advancements in the Mechanical Engineering.
Good afternoon from my side as well. I am Piyush Raj from Mechanical Engineering Department, batch of 2K20. And I would like to welcome our Honorable Director Sir, Dr. D.K. Singh Sir, our Head of Department, Professor Dr. S.K. Singh Sir, our Speaker, Gautam Sarkar Sir, and all the other professors and participants present over here.
Before moving towards the session, I humbly request you all to please follow some basic guidelines to make the program more interactive and more interactive as possible. We request you all that kindly use chat box for any of your queries. Write down your queries in the chat box and we will take it at the end. You can also raise your hand and we will unmute you. Thank you so much for your cooperation and patience. Please be connected till the end of this exciting session. Now, without wasting much time, we take further. Now, I would like to introduce our eminent speaker, Gautam Sarkar Sir, CTO, Head of Strategic Projects, ArcelorMittal, Europe, on the topic of green steel.
So, in the present world, climate change is a thing that we witness and of which everyone looks concerned about. Steel is one of the important parts of the development, but it is also responsible for the climate change. The common takeaways of green steel was that it is simply the steel which has lowest carbon footprint currently possible. It is the process that leverages high temperature reactions in electric arc furnace, steel making to transform waste tires and plastic in the production of high quality steel. In the production of green steel, hydrogen made from renewable energy replaces fossil fuels. Traditional steel production contributes to the 7% of the total greenhouse gas release. Taking a step forward towards sustainable development, green steel has instilled a hope for a better future now. Now, I would like to ask Gautam Sarkar sir to please carry on to the session.
Thank you to both of you, and very good afternoon to Director Sir, all other faculty, seniors, professors, and eminent personalities in BIT SINDRI, and I think there will be some of the students also. So welcome to all. I am also very happy to see Dhaneshwar, who was my batchmate in BIT Mesra, who is now in the professional fraternity in BIT SINDRI. I think Dhaneshwar is on the call. So a very quick background of me. My name is Gautam Sarkar. I am a mechanical engineer from BIT Mesra, 92-96 batch, 96 pass out. And then I am now 25 years with the industry, mostly in the core sector. So my dream was always to work for a steel company, which was the reason to join mechanical engineering in BIT Mesra. And then 10 years after passing out, I was with Larsen and Toubro L&T in India in various sites. Then I was also with Tata Steel for some time, and then very short term in a cement company in Italy. And for last 12-13 years, I am with ArcelorMittal, global steel conglomerate. So 5 to 6 years around in India of engineering, and then I shifted around 6 years back to Europe as a CTO for engineering functions. This is my brief background. Now, in the beginning, as you have already given us a guideline that if there are some questions or something coming up in your mind, you feel free to put it on the chat box. We'll try to check it, and then the whole structure, let's do like this. We have 1.5 hour time, so a bit of planning. I will take around 45 to 50 minutes time to go through a small pack which I have prepared for you, and then we will open the discussion for, let's say, 20-25 minutes if there are some topics which you want to go further, zoom in, and want to know some details. This is, I would also like to add that this is not the end of it. It's very good. The industry and institute cooperation, it is, if it is on a long-term basis, is better. We are coming from institute, and we always want to give it back to the institute. I went several times to my earlier organization, of course, for campus and other campus interview and other purpose, but it's very nice that if we can really give back something to the institute and try to make a strong collaboration where two ways we can benefit from each other. So I would like to straightway jump into the topic. I will try to share some slides to see that. Can you see the screen?
No, sir, it's not visible right now.
Okay, just a minute. Is there now?
Yes, sir.
Yes, sir.
Okay, so the topic today, green steel. We know all what is steel, is green. What are we going to talk about? Already very nicely you have depicted in the beginning. The world is changing now, so we will also have to change. A brief content. We will have a very short safety pep talk. Generally in our industrial fraternity, especially in the steel, which is a very hazardous manufacturing area, we try to capture safety as an integral part of the process. And in our present company, present organization, also when I was in Tata Steel, it was very deeply inculcated in the culture. So what we do, we try to start any meeting with a short safety talk on any topic which is related to safety. Then we will glance through how the world still looks like now, what are the backgrounds, how it has been historically made the evolution, what are the recent trends on energy, how the carbon is related to the overall steel manufacturing, and what we have to do now for decarbonization and the green steel topics. So to capture on the safety issues, I selected a topic which is very relevant, and today our world, we cannot imagine without this topic, which is a mobile phone. So huge users, more than 7 billion people subscriptions in the world today, and on an average we are spending a lot of time, irrespective of the age, from a very childhood stage. Now we are using the cellular phones, especially the smartphones. So what in fact happens, many of us definitely know that from the caller to receiver there are several transmission towers. There is one base station near the caller, there is a base station near the receiver. In between there is a switching station which takes the signal and transfers to the next base station. All these things happens to an electromagnetic wave, so there is a radiation. So when we are calling as well as when we are receiving calls, there is electromagnetic exposure, and the impact you can see on the top left. After 10 or 15 minutes of talking on a phone, what kind of thermal exposure. This is the thermal scanning of a person after 10-15 minutes usage of the phone. You can see the thermal scanning is quite high there, and this is one of the reason that huge radiation exposures which are causing the DNA damages in our body. There are many other factors of DNA damage. For example, excessive smoking or excessive toxic environment, stress, many other things are there. So this electromagnetic exposure is also one of the element of DNA damage. And we all know when the DNA starts damage, the mutation happens, and that is where the inflammation comes and the chronic diseases takes place. For example, the cancer. The number of cancers increase today. I'm not saying for mobile phone, but of course due to a lot of DNA mutations which is happening due to DNA damage by various exposures. So quick idea can be which is given in the bottom, that of course we cannot live without mobile phone. Our whole society is such structured now that we have to live with it to a certain extent. but then we can minimize them. For example, using the handset, some small tricks which you can use, like hold it in the bottom. Why? Because most of the signals are coming and receiving from the top side. So uh, if you block this, more radiation will enter into our body. Then talking near a window where the signals are very clear. Then as much as possible be short and articulate. So these are some of the points which we can always take care while talking to the phone. Okay. So far I am audible?
Yes, sir.
Yes, sir.
Okay. Now I go to the next topic. So again, steel, why do we are so much talking about green steel and decarbonization for the last 2 to 3 years, especially, and in the days to come? One of the main reason is the climate change. We know, all of us in this call know what is climate change and what is going to be the impacts. Tons of informations are there. All the experts are rushing. The world leaders, many world leaders are in a panic mode now. And whether it is melting of the ice in Antarctica, or melting of Arctic Ocean, or permafrost, or exposure of many marine life getting extinct, many life on the earth, on the land also getting extinct. 600 million people staying on the low sea level in the world, they are at the risk of getting under the water very soon. For example, the countries like Bangladesh, some part of Indonesia, they are going to be underwater very soon. We all know this. There was a big initiative taken 5 years ago, 6 years ago in Paris Agreement, where everybody vowed that we will keep it within 1.5 degrees Celsius. But it's just 6 years time, and we are not there. We are much more than what was promised at Paris Agreement. That's the worry point. And the way the progress is going on, the energy usage, the fossil fuel component in the energy, our lifestyles, our overconsumptions, these are leading to a point, tipping point very soon. You may be knowing on 31st, 4 days after today, the next COP26 is starting in Glasgow in UK, where more than 250 world leaders are again joining hands, and experts are saying this is our last chance to rectify ourselves. So some very strong measures have to be taken in order to save the earth. Why? Because as I said, this is perhaps going to be our last chance, and already we know our next generation is at a very, very vulnerable situation. A little bit about steel. Steel is a very, very old element, and it's almost a pillar of our society, because we became more civilized when weapons, not weapons, tools came, wheels came, and by the tools we became, our energy from our biceps went into our neurons. So we became smarter to collect the food, store the food, and also to move around in the earth. All these things were possible by only the steel. Now, the intrinsic quality of the steel is very much affinity towards oxygen. So it is always in the nature in the form of two oxides. We know ferric oxide and ferrous oxide. And when we want to extract this iron from the steel, iron is, we know, the vital part, the main component of the steel. Steel is just an alloy of iron. And iron, to take it out from the oxide, we need to reduce it because it's with the oxygen. And in the process of this reduction, a huge amount of energy is needed. By the atomic structure of that particular compound, it is very natural. Now, this energy so far from the beginning has been mostly on the coal, because coal has been the most easily available, extractable, and quick deployable energy source in the world, and still today it is. If you see the graph on the right hand side, top right, you see coal over last, this is just a graph of last 25 years, but over several decades, coal has always been the main component of the energy to reduce and make the steel from the iron oxide. And this is where most of the carbon dioxide or carbon comes into the steel process. So generally, you see there's a huge amount, 22 to 21, around, let's say 20 gigajoule per ton. 20 gigajoule per ton is the energy which we need for the steel to make the steel. This is quite a lot. Now, if I go to the next one, this gives you the more holistic view of the energy, how energy, from where it comes and where it goes. It's very clear from this Sankey diagram on the left that most of the energy is coming from coal, very little coming from renewables and nuclear now, and then also from the oil. So the coal and oil, both of them are fossil, coming from the fossil sources. These are the major sources of our energy now, which is the concern area. So what we can do in the future, the good news or silver lining is we have started realizing it, and there are solutions on the table. Not everything on the industrial scale. Many things are on the pilot. Some of the things are still in the laboratory, but in the coming days, with the process, with the progress which we are making, of course, we will need a lot of collaboration between all the stakeholders, including the engineering colleges, even first year students of engineering colleges. When they enter into the university, if they are given some very exciting this kind of projects into the portfolio, and then with the industry collaboration, if we are able to come out with some solutions, this will be a very inclusive element for the future. If we typically see the spread of the steel overall in the world, globally, it's around 1.8 billion ton steel is being produced. So it's 1,800 million tons. To give it a perspective, India is producing now 100 million ton, which is, number 2 in the world now. There is a very much skewed figure, because you see China is 1 billion ton. So out of 1,800 million, 1,000 million is only by China. And then the gap between India and China, you can see 10 times. Although we are, India is just on population 1.3, 1.4, just behind China, not very far away. But in steel, India is 10 times lesser than China. And although it is number 2 in the world, but even then, given the population of the India and given the demography of the population, that means it's the youngest country. So more than 500 or 600 million people are still at the young age in India. And the young generation is the most powerful in India. So this gives a very clear-cut future outlook, that with so much of young generation, the work, the job, the need of the house, need of the roads, the infrastructure will boom up. Definitely it will boom up in coming days. It's just a matter of time when India is going to be surpassing everyone and become a very, very dominant steel player in the world. Today it is just 100 million ton, but in the coming days it is going to be definitely number 1 in the world with this kind of population demography. So that makes it more important for us to make our resources accordingly to tackle the huge amount of projects. When we say it will go from 100 million to 500 million, now steel is a very, very capex intensive industry, and it takes time to make a project. A typical project in the steel area, whether it is iron making, steel making, or caster in the downstreams, is generally 24 to 36 months. So it's it's not a quick something which we can do quickly. It takes time and it takes a huge capex. Each million ton needs around 500 to 600, let's say 5 billion to 6 billion dollars, which is around, let's say 7,000 crore Indian rupees in Indian rupees for 1 million ton. This is the industry average benchmark. So you can imagine if we do 100 million ton, how much capex we have to inject there. So this does not come overnight. So these are the elements which will definitely come in the near future. Now we zoom into CO2 topic. So last year globally we emitted from Earth 34 billion tons. So you can see the left top chart. There are two things here. You can see a sudden drop from 2020 to 2019 to 2020 because of the COVID. So the COVID, and then the industry, the transportation, the airline industry, a lot of industry also scaled down. That was one positive impact of COVID on the environment. But then you can see this graph in last 50 years, especially in last, let's say 30-40 years, we are going exponentially and without any control. So if this is going, it is a trend. It's because of a temporary drop because of the COVID. Then we will see in 2021 it will again go up because most of the industry has opened up again. And in this way of exponential growth, you can correlate with this Paris Agreement, where if we are more than 2.5 degrees Celsius with respect to 2018, then it's already a few feet of sea level is going to be higher than the presenting one. So it's the do or die situation now. So that makes it very important that the major industries which are or the major areas which are the contributing to this greenhouse gas or CO2 had to take a call now. So middle chart shows you on the electricity and heat generation. Out of this total 35 billion tons, 35% around is from electricity and heat. So when I say electricity, means the coal-based power plants. Today, if you come to France, let's say 90% of them are nuclear power plants. But if we go to China or India, we are far away now. We are still talking about coal-based power plants mostly. There are some exceptions, but mostly we are still in the coal area. So that is, if the power is not green, power is black, and then this power is being used in the steel industry at a rate of, as I show you, 22 gigajoule per ton. And then steel process itself is a very, there's a lot of CO2 coming out of steel process. So one is the power which steel industry is using, which is coming from coal, and then the process itself is generating some CO2. That's why steel industry is one of the area where all the experts, industry leaders, and big organizations has taken a pledge, a vow that we have to go down very quickly now. Yeah. So what we have to do? There are several international associations like World Steel Dynamics. There is an association in India for steel manufacturing. There is an association in Europe called Eurofair. All these associations at regional level or global level, at this point, in this particular agenda, they are all together and united. It's the voice of everyone that we have to go step by step decarbonize. Now, this is not, when we talk about 1.8 billion ton of capacity, this is not one day's job or even 1 year's job. It will take few decades. As I said, this is capital intensive as well as it is the whole process takes time. So, but good thing is we have the plan now ready. So what are the plans? The first one is process optimization or energy efficiency or waste heat recovery boilers or heat recuperations or less and less flaring into the atmosphere. So if we, by several industrial, industry 4.0, digitalization, automation, and then incremental small improvement projects, if we do, If our process becomes optimized, our specific consumption of energy goes down. So ultimately, it has a positive impact on emission. Then comes the process change. This is a big ticket item. In the process change, I would like to concentrate on the right top corner. This graph you see, steel has evolved. The typical industry of steel was very primitive even few decades ago. We started from small cupola furnaces 200 300 years ago. It was being done in a very crude and primitive way. Then LD Bessemer process came from 30 to 50 maximum tons. Now we are at 400-ton heat size with the LD Bessemer process. So when this huge capacity scale up happened in terms of LD converters, when we are operating at 400-ton furnace, or let's say 350-ton converter, the energy, logistics, many resources getting optimized. And then the electric steel came into picture. It came into picture in just less than 100 years ago. And yeah, again, a few decades ago, direct reduction came into picture. So oxygen converter is still the best route. Still, it is the most popular route because of the versatility to use the hot metal there. But electric is also picking up now. So there are a lot of benefits in the electric arc furnace, which is the alternative for conventional BOF route, and DRI is for the blast furnace replacement. So we will talk about it in the next slide. I have a specific slide for it in the next after a few slides. But the main idea behind this, let's say, simulation is to explain that there are several initiatives are on the table, and on the timeline also this is very clear now for most of the people in the industry, be it in the organization, R&D institutions, even the educational institutions, the big universities. They are also working with us. Universities in US, Europe, and also in India. I know many universities are cooperating with the organizations to have these pilot projects done in their facilities. For example, the big one is in the bottom, shift from carbon to hydrogen. So today we are not able to manufacture and store hydrogen at a big scale, which will be needed for industry, and the process itself is also not stabilized. We are doing it by electrolysis today. It's very expensive, and it's not relevant to do it on an industrial scale. And this is on the laboratory now. So of course, this needs a lot of collaboration with all the stakeholders, including people and expert, eminent professors, and our talent pool from universities like you, who will come and join hands and try to lead this kind of pilot projects. Yep. This slide is to show you typical process routes, what happens in a steel integrated steel plant. So we start from, by the way, are you able to see the slides? Okay.
Yes, sir.
Okay. So you see in the steel, in the integrated plant, we start from the raw material coal, and then it comes to the coking plant. Sorry. On the other side, we have here the iron ores, which are coming into the sinter plant, where we do the agglomeration, and both the sinter and coke, along with some additives, comes into blast furnace, and from blast furnace we come into the BOF, which is LD converter. We make the steel there, oxidation process. Before this, in the blast furnace, it's a reduction process where you take the iron out from iron oxide, Fe2O3 and Fe3O4 both, and the liquid pig iron, or hot metal we call it in your steel language. Hot metal comes in the form of liquid form, which has as high as 4% carbon, comes to converter. There we treat it with very high velocity and 99.9% purity oxygen. We blow oxygen here, and this is an oxidation process. So, and we make steel here. After this, steel, when the steel is tapped, it is already around 0.15 or so carbon. Carbon is reduced there. And then this liquid steel is tapped and it goes to the secondary metallurgy, where we add, as per the grades needed for the downstream, the alloying elements. It also acts as a temperature barrier to maintain the temperature, and some other fine treatments like vacuum tank degassing, RH degassing, or argon treatment, all these kind of treatments for the specific fine tuning of the steel grades. Then it goes to the caster, and then after casting, either we go to the slabs for the flat, or we go to the billets or blooms for the longs, and then from the slab caster we go to hot rolling mill for coil, and we go to wire and rod mill, and then from a hot roll coil we go to downstream cold rolling mill. Then there are a lot of other downstream facilities. But the topic here, you see these red figures. These are the carbon dioxide emission at each process. So when I say the blast furnace here, you see 1.2, almost 1.3 tons per ton of liquid steel. So that means this area, the primary steel making, you can see here most of the CO2 is coming from the primary side. And in the primary, we have the blast furnace is the most CO2 producing area, followed by the BOF. So typically, per ton of steel produced, as a world average, let's say it's 1.8 to 1.9 tons of CO2 is produced. So if we are producing 1.8 billion tons of steel today in the world, it's 1.8 into 2, around 3.6 billion tons of CO2 is coming from steel industry. This is the rough calculation. But then 1.8 billion ton is the installed capacity. Today we are not using that capacity. The actual production is a bit less. But the point here is what we have to do. So we have to attack the area where CO2 is more CO2 intensive. So the solution is on the right hand side, where you see step by step. As I said, it cannot be done overnight. It has to be done step by step, and we have to manage the transition phase. So maybe the transition phase is in between, where we are replacing step by step each blast furnace by a DRI and each converter by an EAF furnace, electric arc furnace. So on the timeline, let's say, for example, our organization where I work today has an open declaration done that by 2050 we will be carbon neutral, and by 2030 or 35 we will interim steps. Similarly, almost all the steel organizations, big organizations in the world, have declared it. And in some parts of the world, this is a kind of compulsion that we have to take some step-by-step announcement at what level we will go down this decarbonization. So we are at BOF now. Our ultimate target is to go to DRI EAF based, and the energy should come from green hydrogen or green power. So when I say green power, no coal is used, only either nuclear or wind or solar or something like this. So we are still waiting for this breakthrough technology. As you see on the right bottom corner, this breakthrough technology, the world is waiting. This is where a very strong collaboration between the industry, university, R&D institutions, and the government, including all stakeholders, is a very good collaboration approach is waiting here, and the world is waiting for it. But in between this end game and today, we have the bridge, we have the transition, where to the large extent possible, whatever is technically possible at the industrial level, we are already doing it. what we are doing, I will try to explain you. Next slide. This is EAF technology. As you see the central picture here, this gives a very good example of steel making. So in the top you see we have BOF, where we have 80% hot metal, 10% scrap or DRI, HBI, whatever it is. We are using BOF, but then BOF is an energy intensive, BOF is a CO2 intensive. In this transition phase, when we don't have the green electricity, green hydrogen, and at the same time there is a scrap is only available in the market. Scrap to the cycle, the steel which you have consumed over last few years or few decades. Generally, the cycle says 20 years. So, steel which you were using for last 20 years, that steel is going to come back in as a scrap. Now, a place like Europe, it's very easy to recirculate the scrap because the collection of the trash, the recycling industry, the procedure, the government systems, they are in a different level in developed countries. But in developing countries, this is not at that level. Many of our scrap which we use in developing countries, they go rusted, they go down the drain. We are not able to recycle it properly. But with the time, the systems will develop. What I want to say here that scrap will not come from the sky. Scrap will come from our usage. So typically, if our steel usage per capita is very low, we will not have much scrap. For example, in India, 1.3 billion, we are only producing 100 million ton, and then some is coming from import also. So on an average in per capita steel consumption in India is very, very less now with respect to the global average. So that means we will have a stage of transition where we, even if we want to implement EAF, which is scrap based, we don't have that much scrap. So there will be a big transition stage where we will have to use hot metal along with the scrap into the EAF. That is why this hybrid is in the concept. So in the hybrid, what we do, we put EAF, electric arc furnace, and we operate it with electricity. And then we put scrap as much as possible, what is available. It should be clean scrap also, because we cannot put anything dump into the EAF. It has to be clean process, non-radioactive, non-other heavy metals. So these kind of things are there. So that the rest of the scrap which is not available, we adjust it with the hot metal, because all the steel plants in India are running in the hot metal non-blast furnace route. So that is why this hybrid concept is here. And nowadays the technology suppliers have come out with various solutions. They have this interim solution also, which they call hybrid, where they are mixing hot metal with scrap and then producing steel. And this is a tested trial method. Many companies in India, also in the world, are using this technology to manage the transition stage. Another important element in EAF is the electricity. We need two main things. One is the good scrap, another is electricity. So when we say electricity, means a very strong grid of both in terms of current and voltage. So many of our grids are not so strong to support the big capacity EAFs. Typically in an EAF, if it is 100% scrap based, we need, let's say, around 350 to 400 kilowatt hour per ton of steel. So if it is a 300 ton heat size furnace EAF, we will need more than 280 or 300 megawatt, 280 megawatt. And then there is also an element of flicker of the harmonics, because the EAF, we have a cycle or a sequence of arcing. So out of the, let's take 50 minutes tap to tap time in an EAF, power on time around 42 minutes. So rest 8 minutes power is not on. And during this 40 minutes of power on time, we have a lot of arcings. So a lot of ups and downs, which creates disturbances to the grid upstream into the main grid. And this disturbances in the grid can create a lot of problem to the other consumers. So that's the reason the grid has to be very, very strong to take these harmonics into the design, so that there is no impact on the other consumers. And this is one of the main issue of when we put the EAF and connect it to the grid, the government grid is not able to support. And this grid, 400 kV or 220 kVs, these are not again one day job. This takes decades because these are cross country, coming from one place to another place. So this is difficult. But then again, for you and me who are working in the technical or engineering side, there are a lot of good solutions available. For example, the IGBT power, digital power now. In the digital power, we are able to go with the power factor of 0.97. I mean the ratio between the active power and the total power is as high as 0.97. So the reactive power is very less. Conventionally, it was 0.8 around. The cos phi was 0.8. Today, the cos phi is as high as 0.97. This is the new technology which is being developed by a supplier like General Electric or ABB. They have these kind of solutions now. So that will bring down the specific power consumption to a large extent. So these things are going on industrial level, and also with some institution, educational universities are there in this kind of research. Left side, the middle picture, if you see this tap to tap time versus productivity and heat size versus the transformer. So the moment I say 300-ton transformer, we are at 240 MVA transformer, 300-ton heat size. If we are at a lower heat size of 100-ton, your transformer rating is lower. So this is also one of the dynamics. So there are many pros and cons, many elements. Ultimate design is taking care of everything and make a balanced design. And this is where the process technology suppliers and industry experts, we are working constantly how to improve the process and how to minimize in the end the emissions. So this was about the EF, where we are doing one element of green steel. Second big element is the DRI. So this is the direct reduction of iron. I think all of us know this, what is DRI. And conventionally we have been using blast furnace, where we put sinter. Sinter is basically agglomeration of fines iron ore. And then we also put some lump ores from the mines. We have lump and fines both. So fines goes to sinter plant and lump goes to directly into blast furnace after washing. And sinter, lump and coke, this we put in blast furnace and we get the hot metal. But this is very, very CO2 intensive. The moment we use DRI, we are bringing down almost 10 to 12% the emission immediately. So what we do in DRI, we charge just pellet. So pellets are coming again from iron ore, and these are actually the fines which are being, or other even blue dust, which is one step below fines. After below the fines, which is in the microns blue dust, we can make pellets by this blue dust through the pelletization plants, and we charge this pellet, and we charge the reducing gas here. So this reducing gas is basically methane, which is being used today. You see, there are two basic technologies. One is coal-based, another is gas-based. In developing countries or even in China, most of it in India is still in coal-based. So coal-based is a rotary clean type, horizontal. We put the charge from the left and we come out from the right. Everything going down along with the coal gas. But again, this is coal. There are some companies in India, I know, they are doing not coal directly, but they are doing by coal gasification syngas, which is coming from coal gasification. But at the end of the day, this is coal coming from coal. On the other side, The new technology which is coming is the gas based now, which is very common and famous in the Western world. In Europe, in fact, coal is completely forbidden, also in some other developed countries where gas is being used, which is natural gas. And as we all know, natural gas is around 84-86% methane, and then we have other hydrocarbons. So this methane is actually the main element here, which is being used as a reducing gas, which enters into this DRI shaft. This shaft is typically, let's say, 130-meter high building. The shaft itself is around 60-70 meter high, which is resting on a very tall structure of 130-meter high, where we are tapping the DRI at the bottom. And then there are several options. We can have cold DRI, we can have hot DRI at 600-700 degrees Celsius, or we can have hot briquette. So if our next downstream EAF, electric arc furnace, is next to this plant within 100 or 150 meters on the layout, we are able to charge hot directly into the EAF. This is what many people are being trying in the industry, to keep this and EAF side by side, so that we can do the hot charging and save energy. This is what we tried to also discuss during the first slide. Energy optimization. So layout engineering, one of also the main element of civil and mechanical engineering department, layout engineering. So what should be the intelligent layout? So that my not only this temperature drop, the water, the sludge, the in materials, out materials, everything in an integrated steel plant is so complicated, and it needs to be planned in such a way with a holistic long-term view, which can have a very big impact on your how you operate the plant. What will be your OPEX? What will be your reliability? What will be your environmental impact? CapEx is not the only thing. CapEx is just one-time expenditure. Once you commission the plant, then it is running for next 40 years. So if a good layout is not done well in the beginning, it is something going to pain for next 40 years if it is not done well. That's why it's important. Also, I think these kind of topics, if we can cover in some way in some selective or elective projects, or include in curriculum, or making an interesting joint venture with some organizations, and trying to give this kind of inputs to the students right from the beginning, so that they also start thinking that, yeah, this is also something where I can go and really contribute to industry, in fact to the society. Yeah. So DRI has several discharge options. If the plant has to transfer it to far away, then we go for HBI. If it is little, HBI means hot briquette iron, you can see in the bottom. And if it is not so far away, we say cold DRI. And if it is just next EAF, next to the shaft, it is hot DRI. So today in the world, we have two main companies, the US-based company called Midrex, and one is Italian-based company called Danieli Ortinova. The whole technology of gas-based DRI is only with these two companies now. They rule the world market for DRI. And yeah, both of them has got some design elements difference from each other, but mostly the operation is same. In the right hand side picture, you see this is from the Italian one, where we don't have a reformer as a separate element, but we have a reformer within the shaft. But on the left hand side, it's the Midrex one, the American company. In fact, this is the technology developed by Kobe Steel of Japan, and now they have a collaboration with the US-based company Midrex. And here you see we have a big shaft, and then we have a reformer. In this, the reducing gas is being reformed, and then gas is being injected. And the off gas which is coming, and the same off gas is coming back into the system, into the reformer, and after proper reforming action, again going back. So this is a circular process here. Yeah. In this process of circulation, there is some delta. and this delta is being made up by injecting natural gas into the reformer. This is how the process works here. So typically, as I said, you may see here $350 per ton is the specific capex almost. So if you are able to make a 1 million ton plant, you can imagine it's $350 million, which is around 2000, I think 2,300 crores in Indian rupees in today's world. So this is the order of magnitude. Important point to see here, you can see the specific power consumption is very less. Electricity is 80 to 100 around. In terms of EAF, you may be remembering it is 350 to 400 kilowatt hour per ton. But here it is very less. Why? Because most of the energy is being used here from the chemical energy. Electricity part is very less here. Yeah. After talking elements, what are the next steps? We have been talking only the transition now. The next steps are several, which is the end game is the green hydrogen. We know that our end game is green energy, where no fossil fuel is being used. It is only coming from renewables. It can be wind, it can be solar, it can be nuclear, but nuclear also have waste, so it's a question mark. And it can also be the hydrogen, because the beauty of hydrogen is when we burn hydrogen, the result is only water, nothing else. So these are on the process, and then again the carbon capture and carbon utilization. So at various levels, these end game initiatives are ongoing. For example, on the left bottom you see the EAF, next generation EAF, where we have a very improved design with oxy-fuel burner. When I say oxy-fuel burner, means we still have a possibility in the EAF today to use the hot metal, as I said. So hence we should have oxygen injection facility also to decarbonize the extra carbon into the hot metal. So that will also reduce the electric energy consumption here. As I said, in every country do not have this strong grid of electricity to support EAF. Till they make the grid, we can continue to use a part of the hot metal as a strategy in the transition stage. Hence, there is an oxygen lancing is required. So that's why the design of EAF, which was not originally there, has been adapted to use a part of oxygen. Similarly, other lot of facilities. The right side, the bottom, this shows the hydrogen manufacturing, which is in a laboratory pilot scale now. On the top, this particular cross section is very interesting, which is again a modified version of EAF. This is called continuous charge, where you see the scrap is being charged in a 90-degree to the furnace on a horizontal way, and then it is entering into a duct, and scrap is getting preheated. So before the scrap is entering into the electric arc furnace, this is already at 200+ degrees Celsius, and this makes less effort on the electricity, and the energy consumption, specific energy consumption, is much lesser here. And this scrap is being preheated by the huge fume, which is eventually coming from the EAF and going into the atmosphere through the back filter. So we are using this backtrack, the fume, to preheat the scrap, and then after necessary primary and secondary cooling, it is being flared. But eventually we are reutilizing the gas and the sensible heat here. This is one of the also very good area of research for all the mechanical engineering students. What are the impact? This is very simply drawn here, but there are a lot of process related challenges here, like VOC materials, the sticking of the scrap onto the metallic conveyor, and the chemistry of the gas here, the chemistry of the iron here, the iron carbon diagram related lot of elements are being practiced here. So this continuous charge EAF is also one of the very interesting area where mechanical engineering can add a lot of values in there. Yeah. So what I covered is just tip of the iceberg, and this is few elements only which I try to share with you, which we are trying to do to make steel making more and more sustainable. Hence, our duty to the earth, in fact, to how to minimize the emissions. Thank you for all your attentions. Now it's we have crossed 50. How much we have crossed? 58 minutes. Yeah, 1 hour. We still have some time. So,
Thank you, Gautam.
I'm very happy to see Dhaneshwar. I remember our old days in BIT Misra 25 years ago. We were in the same hostel. Hello. Okay.
Sir, you are muted actually, Dhaneshwar sir.
Okay, Gautam, lot of thanks for briefing your knowledge or disseminate your knowledge to our students, and hope this will be beneficial for the researcher and our student also for CO2 removal and green steel technology. And thank you. Anybody has any queries about this green steel technology, please ask to the Gautam Sarkar.
So if from participants anyone is having any query, then you can ask to our speaker.
Yes, of course, sir. You can ask.
Hello,
Yeah, Sunil Kumarji, boliye. Tell me, please.
sir. If you are remembering MIT Muzaffarpur, we went from Moria Express.
Oh, yeah. I
And
remember.
only on the first day you return back in Burma Lodge.
Okay. Yeah, now I remember. In fact, I remember everything. It was, yes, in fact, a
So
few hours
I'm
I
also here only BIT Sindri itself.
Okay. So you are in BIT Sindri now?
Yeah.
Okay, very nice. So maybe we can touch each other later on. Dhaneshwar has my number, so let's.
Okay. Just recall I have talked to you.
Sure.
Okay, thank you, sir. Thank you.
Thank you. So maybe Dhaneshwar has my number. This is just our first interaction. This is just the beginning. I will not say the end. So whenever any one of you, any kind of research idea, any kind of interaction you want to do with the industry, or on my personal basis, or through my organization, if I can help this fraternity, the professors and the eminent researchers, I will be very much happy.
Okay, thank you, sir.
Yeah.
Anyone having any queries, you may ask now or write in the chat box.
So, I don't think that
Conclude
any.
the session. Yes. Please conclude the session now.
Yeah. So thank you so much, sir, for such an insightful session and intuitive session. Gautam sir shared with us a lot of informative things during the session, a few of which are, sir told us about the harmful effects of electromagnetic radiations that we are exposed to during using our mobile phones. He also told us about the harmful effects that it will be having on the aquatic life as well. He told us about the distribution of the iron production. Out of the 1.8 billion tons, 1 billion ton is produced by China, and India being second produces only 100 million tons. By 2050, 1 by 5th of steel production will be from India compared to 5% now. Sir told us about the problems that industries are facing in EAF and also told us about the new technical solutions that are being adopted all around the world. At global level as well, the organizations are taking various steps like the Paris Agreement of 2015, where countries agreed on the temperature less than 1.5 degrees centigrade, but we could not hold to it. Sir also detailed us about the DRI, direct reduced iron, the process, and also the elements that we are using and the problems we are facing. Thank you so much, sir, for this intuitive session. It was quite fascinating to know about you, and the insights you shared with us were extremely knowledgeable. We all are blessed to have you here as our speaker. Thank you so much, sir, for spending your valuable time.
Thank you, and namaste.
Um, As we are moving towards the end of this session, I would like to thank our prominent guest speaker, Director Sir, HOD Sir, Associate Professors, Researcher and PhD scholars, and all the other professors for joining today's session and making it quite successful. We will be meeting tomorrow on the same platform and at the same time with Dr. Anil Chand Mehto sir and Dr. Shiv and Prajapati sir as our guest speakers. So let's meet tomorrow. Until then, please be safe and healthy. Thank you so much everyone for joining. Do fill the attendance form from which we have